Hi everyone. Today we are going to do the session 2 on the analysis of the T-beam from the subject Design of Reinforced Cement Concrete. The tables of content. So let us have the recap of the equation. We will solve the problems, then we will solve MCQ question in order to refresh the concept. Formulas. So in IS 456 there are formulas. In RCC there is no need to remember most of the formulas. We will get obtained from the code. So if you go to the page number 96, there is a formula so named flanged sections. So here you can obtain the formulas for the T-beam. So in order to recap, so we will calculate the XU, that is the depth of the neutral axis. If it is less than the DF, then the T-beam will be the beam of size PF by D. So then we can use the same formulas which we use for the beams for calculating the moment of resistance or the steel AST value. So here in the same page the formulas are also there. So see, using this we can calculate the XU. So first assumption is that XU lies within the flange. So case 1, that is. So we will calculate the XU. If XU is less than the depth of the flange, then we will continue and we will calculate the moment of resistance, and we can calculate the moment of resistance using this equation. If this XU is greater than DF, then we will come to the second part, that is, actually here it is not there. We have to use the relation C1 plus C2 is equal to T. So that is the compression force in the wedge plus the compression force in the remaining part of the flange, so is equal to the tension force. So using the C1, C2, so we have to calculate C1, C2 and T. So in that relation actually we will obtain the XU. So that XU, if it is greater than DF, then it's okay. So we will proceed further. If that XU is less than DF, for the same equation C1 plus C2 is equal to T, the C2 value there changes. Instead of DF, we will replace it by the equivalent term YF. So where YF is given as 0.15 times the XU plus 0.65 times the TL. So this value will substitute and calculate the XU. So if XU calculated, we will compare with the XU max. So the maximum value of the XU for 250 grade steel, it is 0.58 into the D. So like that we have the XU max values. So those XU max values we will compare with the XU max. So if XU is greater than XU max, then the section is over reinforced. So once the XU is greater than XU max, then we will come to the equation G2.2. So then we will compare DF by D. If DF by D is less than, does not exceed or equal to, less than or equal to 0.2, then we have to use this equation. So using this equation we can calculate the moment of resistance of this section. If DF by D exceeds the 0.2, then use the equation in page number 97 and calculate the moment of resistance. Okay, for over reinforced section. If it is under reinforced section, means that is XU is less than XU max, then what we have to do is we have to check DF by XU. If DF by XU is less than or equal to 0.43, then go back to this equation. So that is G2.2. So here instead of XU max, replace the XU max by XU. Same formula. So just their total they are given once. They will not do repetitions. So just we have to change XU max to XU when XU is less than XU max and DF by XU is less than or equal to 0.43. Then we have to use this equation by replacing XU max by XU. Okay. Then if DF by D ratio is greater than 0.43, so use the equation which is here in G2.2.1, replace XU max by XU. Then you will get the moment of resistance of the under reinforced section when DF by XU is greater than 0.43. Okay. These are the equation. Using this equation we can solve the problem. So problem number 1. So actually this problem I have solved in last class also. So in order to we'll recap it firstly. So here we see a singly reinforced slab, depth is 120 mm. So slab is nothing but the flange. So slab acts as a flange. So that is the depth of the flange is 120 mm. Next is supported between the beams 3 meter to 3 meter, means the slab length is 3 meter. So if you want to calculate the effective width or something S1 by S2, then we can use it here. So I have not written here in this one data. If it is required, we will use it later. Then the width of the rib is 450 mm. So that is BW. So width of rib or width of web. Then D is the effective depth is 550 mm. D is small d is 580 mm. Then the effective cover is given as 50 mm. So here the effective cover of the steel bar in lower tier is 50 mm. The effective span of simply supported beam. So don't confusion between this span and this span. So here clearly they are given effective span of the simply supported beam is 3.6 meter. So here L is equal to L naught is equal to 3.6. L naught is the distance between the points of zero moments that we have seen. So they were asked to determine the depth of the neutral axis and moment of resistance of the T-beam. So I have written FCK Fy, okay, note down. So you have to calculate the steel. Since the steel is not, they are not given directly, they are given in terms of the bars, number of bars. So 8 bars of 20 dia. So to calculate the area of the circular bars, so or circular sections, so the formula is pi d square by 4. So we will substitute the diameter over here. So here 8 is the number of bars. So n into pi d square by 4. So 8 into pi d square by 4. If you calculate this, the AST will be 2513 millimeter square. Okay. So next we have to calculate the effective width. See in the last problem they are not given the effective width. So effective width is calculated as using the formula. This is given in page number 37 of IS 456. So once again you have to see the IS 456. So L naught by 6 plus BW plus 6 times the DF. So here you see it is in meter. So L naught is 3.6 meters. So divided by 6 plus BW. Width of the web is 450 mm. So you have to divide by 1000 in order to convert from millimeter to meter. So divide by 1000. If I divide 450 by 1000, I will get 0.45 plus 6 times the DF. So 120 divided by 1000. So 6 into 0.12. So 120 divided by 1000 will be 0.12. If I solve this, I will get BF as 1.77 meter. So we will go assume that depth of the neutral axis lies within the flange. That is the case 1. So first assumption. So XU is less than DF. For that we will calculate XU. So XU is given as, so this you can obtain by the page number 96. So 0.87 Fi AST divided by 0.36 B into FCK. So 0.87 into 250 into AST is 2513. So directly it is not there in the page 96, just we have to modify this. So multiply this by AST divided by 0.36 into B. See here B is 1.77 meters. So from meter we have to convert into the millimeter, that is 1770. Okay, multiply by the 1000. Meter to millimeter is multiply by 1000. Millimeter to meter is divided by 1000. So multiply by FCK. So if I solve this, I will get 57.19. So calculator numerator separately, denominator separately, and then divide. So then we will get 57.19 mm. So ಎರಡನ್ನು ಸಪ್ರೇಟ್ ಆಗಿ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿಕೊಂಡು ನ್ಯೂಮರೇಟರ್ನ ಸಪ್ರೇಟ್ ಇಟ್ಕೊಳ್ಳಿ, ಡಿನಾಮಿನೇಟರ್ನ ಸಪ್ರೇಟ್ ಇಟ್ಕೊಳ್ಳಿ. ಸೊ ಆಮೇಲೆ ಡಿವೈಡ್ ಮಾಡಿ. ಸೊ ಕ್ಯಾಲ್ಕುಲೇಟರ್ ಯೂಸ್ ಮಾಡಬೇಕಾದ್ರೆ ಕೇರ್ಫುಲ್ ಆಗಿರಬೇಕು. ಸೊ ಮೋಸ್ಟ್ ಆಫ್ ದ ಟೈಮ್ ಸೊ ನೀವು ಕ್ಯಾಲ್ಕುಲೇಟ್ರಲ್ಲಿ ಸಾಲ್ವ್ ಮಾಡಬೇಕಾದ್ರೆ ತಪ್ಪು ಮಾಡೋದು. ಸೊ ಹಾಗಾಗಿ ಎಚ್ಚರಿಕೆ ವಹಿಸಬೇಕು. ಸೊ 57.19 mm, this is the value of XU. So I have to compare this value with the DF. So this XU value is less than DF. Means DF here is, what is the value of the DF? So that is actually 120 mm. Okay. So it is less than 120 mm. So what assumption is correct? What we have assumed, XU is less than DF. That is correct. Then we will calculate XU max. So you see here XU max is 0.53 times the D. So why 53? Because the grade of the steel is 250. So 0.53 into D, so that is 580. This is 307.4 mm. So if I compare XU with XU max, XU is less than XU max. So the section is under reinforced section. So then for the under reinforced section, so in order to calculate the moment of resistance from the page number 96 of the ES code, so I will pick the formula and I will write down the formula over here. So this formula, for this formula I will substitute the values. See here, Fi, grade of the steel is 250, AST, so that is the tensile steel area. So 2513.27, so into depth, effective depth is 580 mm. So 1 minus AST 2513.27 into grade of steel is 250. So BF, so last time I have told that is in meter, multiply by 1000, so that will be 1770 mm, 1770 zeros, multiply by the 580, that is the depth, into 50. So solve the bracket term first and multiply by it, so you will get the ultimate moment like this. See, when you calculate using the calculator, so scientific calculator, so you will get a bigger term, 30411 something, so you will be getting that. So you will not getting us into 10 power 6 sometimes. Then you have to use ENG, so press ENG, so 1 or 2 times, so then the calculator will show like this, 304.11 into 10 to the power 6. The unit is Newton millimeter. So every time you have to note down the units, so that is very important. So this 10 power 6 Newton millimeter can be written as kilonewton meter. So 304.41 kilonewton meter is your moment of resistance of the section. So neutral axis value is 57. So XU is 57.19 mm. Depth of neutral axis value, moment of resistance is 304 kilonewton meter is the moment of resistance. So that is the first problem. So come to the next problem. So here we have to calculate once again the moment of resistance of the T-beam. So I have the following sectional properties. Grade of steel is M20 and grade of concrete is M20. I think I told steel. So and Fe45 415 HYST parts. So steel grade is 415. So width of the flange is 1300 millimeter. Thickness of the flange is 100 millimeter. Width of the rib is 325 mm. Effective depth is 600 millimeter. Area of the steel is 4000 millimeters square. They are directly given. So width of the flange, it is not plane, it is flange actually. So width of the flange is this one, BF. So this figure they are not given. So if they have given, that will be very easy. So actually we know the shape of the T-beam. So BF is this one. So BF is 1300 millimeter square. So I have written in the data. Next, thickness of the flange. So this is the flange. Thickness of the flange is DF. So I have written DF as 100 millimeter. Next, width of the rib, that is BW, is 325 mm. Width of the rib is this one. Then effective depth, this is the small d. Small d is 600 millimeter. Then cover they are not given. Area of the steel, that is the tension steel. So AST is 4000 millimeter square. So we have to solve the problem. So effective width they have given. Last problem we calculated the effective width, but here they have given. So AST also they have given directly. So no need to calculate, no need to do those two steps. So what we'll do, we will assume that actual neutral axis lies within the flange, that is XU is less than the DF. So we'll calculate the XU by using this formula. So the XU value, when you substitute the values over here, so it will come to as 154.3 millimeter. So this value actually is greater than DF because our DF value is 100 mm. So what the assumption we had made is wrong. Actually, the neutral axis is lying in the web. It is not lying in the flange. So in order to see what is the real value of the XU, so you will use this relation C1 plus C2 is equal to T, compression force 1, that is the web, plus compression force in the remaining part of the flange is equal to tension force. So C1 is given by 0.36 FCK XU into PW. So you can see the page number 96. By little modification you can get the value of the C1 formula there only. So 0.36 FCK is 20. So actually BW is 325 mm. XU is the unknown value. So here C1 will remain. So if I solve this, I will get 2340 times the XU because XU is unknown. So C2 formula is 0.45 FCK. C2 is the remaining part of the flange, the compression force in the remaining part of the flange. So 0.45 FCK, BF minus BW into DF. So here all the terms are known. So FCK is 20. So depth of the flange is 100. So BF is 1300 mm. BW is 325 mm. So if I solve this, I will get 877,500 Newton. There is no need to convert to kilonewton. So let's keep like this. Then tension force is equal to 0.87 Fi into AST. So to calculate the tension force, Fi we know grade of the steel is 415. So into AST is 4000 millimeter square. So there is no need to conversion. The tension force will come out to be this value 1,442,00 Newton. So these are all direct calculation in calculator. So there is nothing to worry. Just so enter the calculator values properly. Proper ಆಗಿ calculator values entry ಮಾಡಬೇಕು. ಒಂದು ತಪ್ಪಾದ್ರೂ problem full ತಪ್ಪಾಗುತ್ತೆ. So C1 is this much plus C2 is equal to T. So we are substituted in the relationship and I will solve for the XU. See, this I will take to the right hand side, so that will be minus. So equation 877,500, if I take this side, so it will be minus. You have to write minus sign. So then, so you subtract this, you will get this value. So 566,700, this value you will get. So this will go to the denominator. So XU is equal to, this will come. So if I solve this, I will get XU as 242.18 millimeter. So after calculating this XU value, we will check with the DF. If it is greater than the depth of the flange, okay, then we will proceed to the step number 3. If it is less than the DF, actually we have to once again recalculate. But since it is greater, we will don't worry about the recalculation. So we will go to the next step. So what is next step? So XU value we have obtained. So we will compare with the XU max to check whether the section is under reinforced or over reinforced. So XU max, this is 415 steel. So 0.48 times the D, XU max is equal to. So substitute depth, so I will get as the 288 millimeter. So XU is less than the XU max. So XU max is 288 mm, XU is 242 mm. So since XU is less than XU max, section is under reinforced. So then go to the codal provision. So codal provision, I will go it under reinforced section. So actually we will check DF by this one, XU value also. So DF by XU, if I check, that will be actually less than the 0.43. So I have not shown that calculation here, directly I have taken the formula. So hence according to the class this one G 2.2.2, page number 96. So moment XU max is replaced by XU. So 96 page number alli irutte. So df by XU no calculate ಮಾಡಿ ನೋಡೋಣ. What is that value? So depth of the flange is here I think it is 100 mm. Am I right? Yes, it is 100 mm divided by XU. So XU is 242, obviously 0.413. So it is less than 0.43. So that's why we'll write this equation. So mu is equal to 0.36 times the XU by D, 1 minus 0.42 XU by D. So this equation is there in the IS 456 page number 96. So G 2.22. So just write down this equation. So after writing down this equation, substitute all the terms. XU, we have to substitute the XU value 242.18. D is 600 mm. 1 minus 0.42 into 242.XU value. So BW, width of the web. D square is depth square, 600 square. FCK, grade of concrete, is 20. So 0.4 times FCK is 20 mm. Sorry, not 20 mm, 20 Newton per mm square. So BF is 1300 minus BW, width of web 325, depth of flange is 100, D minus DF by 2. Okay. So solve this bracket term first. So divide this one, then we will obtain first term as 282, 55, 72, 18. The second term we will obtain as 48, 26, 25, 000. So you can solve it using the calculator direct. So just as first solve the bracket term first. So 1300 minus 325 you calculate. 100 divided by 2 is 50. 600 minus 50 is 550. Then you multiply from year to year is this symbol. So this one, this value, from year to year you have to do this one. So then the ultimate moment of resistance value, if I add these two, I will get this one. So press ENG in the calculator. So you will get 765.18 into 10 to the power 6. So I have told in the last problem, this can be written as kilonewton meter. 765.18 kilonewton meter is the moment of resistance, or the ultimate moment of resistance of the given T section. Okay, another problem. I am solving another problem. So all types of the problem we will be solving. So in order to have this one, so idea, calculate the ultimate moment of resistance of the T beam using the following data. So read the data here. So directly you can write it down. So it is also as the previous problem, it is they are given directly. So read the problem. Reading the problem is very important. So problem na correct ಆಗಿ ಓದ್ಕೊಂಡು ಡೇಟ್ ಅನ್ನು ಕರೆಕ್ಟ್ ಆಗಿ ಬರ್ಕೊಳ್ಳೋದು ತುಂಬ ಮುಖ್ಯ ಇದೆ. So see here, width of the flange BF is 1500 millimeter, depth of the flange is 100 millimeter. So overall depth is 600 millimeter. Next, width of the rib or web is BW is 300 millimeter. So area of the tension steel is directly millimeter square. Effective cover 40 millimeter. Why here they are not given the effective depth? Actually small d they are not given, so we have to calculate that. So next, FCK 15 Newton per mm square. Grade of the steel is 415. So small d is capital D minus the cover. So 600 minus 40. So 600 minus 40 is 560, that will be. So as usual, so we will assume that first XU is less than the depth of the flange. So for that we know the formula. So we will substitute all the terms in the formula and we will calculate the XU. The XU value works out to be 109.42 mm. So this is greater than DF. So our assumption is wrong. So next we assume that the neutral axis lies below the flange. So we will calculate the C1 value, C2 value and tension force. So C1 is given by this term So here XU is unknown, that term will remain. Once again I am telling, FCK is 15, so width of the web is 300. I will substitute and I will multiply. Here capital X symbol represents multiplication, don't confuse. So because I can't write the term continuously, so 1620 times the XU, C1 will be coming as. C2 is, so the compression force in the remaining part of the flange, 0.45 times the FCK, BF minus BW into the depth of the flange. So I will substitute. All the terms are direct terms, there is no need to worry. So substitute the terms, solve the equation, first solve the bracket, then multiply it, we will get 81 4 zeros followed by 4 zeros Newton. Okay, tension force is 0.87 Fi AST. So I will substitute, I will solve for the XU. See, I calculated the XU value. The newly calculated XU value is less than DF. So we have to actually recalculate it. So actually XU, if it is less than DF, we have to recalculate the XU by changing the term in the C2 value. See, C2 value changes. So C2 value changes. C2 is equal to 0.45 times the FCK, BF minus BW into DF was the earlier formula. We will write it as YF. So if it is greater, then no issue. So we will go to step 3. So if it is less, then we have to recalculate it by introducing a new term called as the YF. So see, last problem XU was greater than DF. We went directly to the next step. This problem actually XU is less than the DF. That's why we are recalculating the C2 value. So C2 value after substituting here, so YF is 0.15 times the XU plus 6.8 times the XU value we don't know. So DF value we know. So YF will work out to be like this. Okay. So C2 is equal to, so solve the bracket term, 1500 minus 300 will come 1200. So 0.45 into 15 into 1200. So this value works out to be 8100. So multiply by this bracket term. So then I will multiply by this one, 8100 into 0.15 will works out to be 1215 XU, because XU is unknown, plus once again 8100 into 65 will work out to be 526500. So in C2 also there is unknown term XU. So once again you will use the same relationship. So I didn't recalculate C1 and T because the value remains the same. There is no need to recalculate. So C1 is equal to, you have already calculated. So that will be, so 1620 times x2. C2 newly calculated value 1215 times the XU plus 526500. T is already calculated. So we will add the common terms. So this I will add. So this I will get it as 2835 XU. This I have to take this side, so it will be minus. That's why the new value is 359877.75. So this XU, this will come to denominator, so we will divide the term. So once we divide, we will get XU as 126.94 mm. So assumption is correct. So dF by XU we will calculate. So dF by XU value is greater than 0.43. So that value is greater than 0.43. Note it down, this one. So assumption is correct. Okay, we will calculate XU max. So XU max is 268. So actually XU is 126.94. So but XU max is 268. So XU is less than XU max. So section is under reinforced. Once again we are under reinforced. So from page number 97, we will go to 97 because see here dF by XU is greater than 0.43. So we will go to page number 97. So that in page number 97, the equation given is for O-reinforced section. For under reinforced section, we will replace XU max by XU. So you have to replace XU max by XU and then you have to write it down. So then write down the equation. So here I have calculated XU by D. So in order to make simple, since it is XU by D, so problem will become simple in order to solve. So substitute all the terms over here. So you have to calculate YF. So actually YF is equal to 0.15 times the XU plus 0.65 times the DM. So you calculate the YF value also and substitute. So YF comes out to be 84.04. So if I substitute in the equation, so I will solve these two terms. So separately, so I will get these values. So and I will add this. So if I add this, I will get 458.16 into 10 to the power 6 Newton millimeter, which is equal to 458.16 kilonewton meter. So kilonewton meter is the answer. So this is the moment of resistance of the your T beam. Okay. So next beam. So here actually once again T beam. So isolated T beam. So isolated T beam means, so in the T beam the slab projected on both the sides, on either side, will be discontinuous, means that is ending. It is not extending to the next beam. So like this, there is no extension. So here only the slab is ending. So that is the new case. So till now we solved actually the continuous slab. So slab is continuous. So here they have given directly isolated T beam. So isolated T beam, flange is 1200 mm by 100 mm. So here we actual width they have given 1200 mm and width of the rib 250 mm. So width of the rib is 250 mm, I have written here, and effective depth small d is 600 mm, tension steel is 350 mm square, grade of concrete is M20 and steel grade is Fe415. So we have to compute the ultimate moment of resistance. So span of simply supported beam is 8 meter. So 8 meter is the span of beam, that is L0. So L0 is 8 meter. Also calculate the safe superimposed load the T beam can carry if the effective cover is 50 millimeters. Okay. So write down all the data, read the question and write down all the data. So actually for the isolated T beams we have the formula. So whatever the B they are given is the actual width. So L0 divided by L0 by B plus 4 plus BW, the width of the web. So L0 is equal to 8000, that is the distance between the points of zero moments in simply supported beam. L0 is equal to L. So if it is continuous beam, L0 will be 0.7 times the L. So substitute the values. So B actual width we have to substitute 1200 plus 4. Solve the denominator, divide this one. So we will get BFS effective width as 1000 millimeter. So note down. So actual width was the given one. So we have calculated the effective width. So for isolated T beam, this also in the page number 37 of IS 456 this formula is. So you note down the formula. So you have to calculate the BF value. So once again the same thing, you have to follow the same steps. First we will assume neutral axis lies within the flange. So use this formula. So we will substitute all the terms over here. So Fi, AST, BF. So actually this is BF. So 1000 millimeter effective width. So BF, then FCK 20. So after substituting here, if I solve this, so it is coming greater than DF. If it was less than DF, then the assumption would have been right. So since it is coming wrong, so okay, we will calculate C1, C2 and the tension force. So using the formula, if I calculate the C1, it works out to be 1800 XU. So C2, if I calculate this one, so it will come in 67 50 Newton. Tension force, so we will be coming this one. So actually I will calculate XU. So this XU value works out to be this one, 327.04 mm. So XU actually is greater than the depth of the flange. So since it is greater than depth of the flange, so we will proceed to the step number 3. So we will calculate the XU max. So 0.48 times the depth. So 0.48 into 600. So we will work out to be 288 mm. Okay. So on df by XU value also I have checked. So it is less than 0.43. So this is XU is greater than XU max. Okay, yeah, right. See, the section is over reinforced. So no need to calculate actually this one. So you have to calculate df by d value. So XU is greater than XU max. Section is over reinforced. Then once the section is over reinforced, so we will check df by d value. So df by d value, so what is the depth of the flange? 100 mm. So 100 mm divided by d. So what is the d value? D value is actually so 600 mm. So 100 divided by 600 will comes out to be 0.166. So 0.166 is less than 0.2. So we will go for the page number 96 and directly write down the equation. There is no need to change XU max by XU because the section is over reinforced. So directly write down the equation, then substitute in this formula. So once I substitute in the formula, so solve the terms. So solve the bracket terms first. So df substitute. So see, okay, I'll turn from first term 0.36 XU max value. You have to substitute XU max value 288 mm divided by d will works out to be 0.48. So that I have written directly 1 minus 0.42 into 0.48. So into d. See here, why I have written 0.48 is, see here. So this is XU max by d. So XU max value is 288. So if I go back, 288 divided by 600 it comes out to be 0.48. So that's why I have not shown here. So 1 minus 0.42. So XU by d. So BW. So width of the web 250, d effective depth 600, FCK 20 plus 0.45 20. So width of the flange we have calculated for isolated T-beam, that is 1100 mm, minus width of the web 250 multiplied by the depth of the flange is 100. So d effective depth 600 minus depth of the flange 100 by 2. So solve this between the plus from here to here one thing. So it will come to 37125 zeros, and if I solve the equation from here to here, so I will get 2483 34 336. This value I will add these terms, so that will work out to be moment of resistance works out to be 619 kilonewton meter. So actually they asked here, along with the moment of resistance, what is the superimposed load that can be applied to the beam. Actually this is quite lengthier problem. So compared to other problems, we have to calculate the load, that is the W, moment. We have calculated moment. So we have to calculate the load, so which you have done in the analysis of the beams. So working moment, whatever we have calculated is the ultimate moment. So ultimate moment divided by the factor of safety of 1.5 will give the working moment. So working moment is this one. So total load will be actually dead load, that is the weight of the slab plus the live load. Live load is the superimposed load. So the load which will be keep changing, means which is not constant, live load is. So whenever there is a occupied area, means like when the person is moving, that will be a load. So person can't stay at one place. So live loads keep changing, but the dead load is a constant load. So what is the maximum superimposed load? Live load is also going to be called as the superimposed load. Whatever the furniture, cots, all these things will come under the live load. That we have to calculate. So moment is equal to WL square by 8. Okay. That one we know because it is simply supported beam. WL square by 8. L is 8 meters. Since it is in kilonewton meter value, I am directly writing this. And since I am substituting this moment in meter, I have to substitute here length also in meters. So 8 meters. So I will calculate W. W works out to be this much. Depth of web is this much. So depth of it is total depth minus the depth of the flange. So self weight of the beam. So we are calculating the self weight of the beam. So BF into DF. So BF into DF, that is the width of the flange, that is the width of the T-beam into depth of the flange, plus remaining. If I take the T section, the top rectangle is BF into DF plus BW, that is the width of the web, into the depth of the web. That's why we are calculated the depth of the web. Multiply by density of the concrete. We will take the density for RCC as 25. So multiply in meters only. So we will get to be self weight of the beam as 5.94 kilonewton per meter. So if I substitute here, the live load which can be applied is, so I will apply it to this equation, that is total load is equal to dead load plus live load. So our total load is here 51.6 kilonewton meter. So self weight of the beam is 5.94 kilonewton meter. So unknown term is live load. So live load is, if I minus this, it will comes out to be 45.69 kilonewton meter. This is the superimposed load. So we will solve the last problem for the session. So determine the area of the tension reinforcement required in the flanged beam. So flanged beam is T-beam. We have to calculate the AST. So actually in the previous problem AST was given in all the previous problems, but here we have to calculate the tension reinforcement having the following sectional dimension to support a factored moment. So moment they are given. So earlier we are calculating the moment of resistance, but here actually the moment they are given, factored moment. So 300 kilonewton meter. So width of the flange is 750 mm. So width of the flange they are given. Width of the rib is effective width. Let us take effective width. Width of the rib is BW is 300 mm. Thickness of the flange is 120 mm. Effective depth is 600 mm. M20 concrete and FA 415 steel. So I return the data. So effective width is 750 mm. Depth of the flange is this one. Okay. See, moment of resistance of the flange. So we will assume that here also the neutral axis lies within the flange. So we will calculate only the moment of resistance of the flange. So if I want to calculate the moment of resistance of the flange, so I will use this formula. So note down this formula, 0.36 FCK BF into the depth of flange into the D minus 0.42 DF. This is ultimate moment resistance formula only. So this formula is similar to your normal beam. So the formula which is used to calculate the ultimate moment of resistance of the beam, the same formula. So instead of depth, so here depth of flange will be written. So XU, I think XU will be there. So instead of XU, DF we will write. So just the same formula, but just change the term DF. Instead of B, we are writing the BF. That is the width of the flange. So 0.36, FCK is 20. So width of the flange is 750 mm into the depth of flange is 120 mm into 600 minus 0.242 into 120. So if I solve this, the ultimate moment of resistance works out to be 356. So if I compare this moment with the given moment, so So whether I have written here? No. So with the factored moment, so factored moment is 300 kilonewton. Say moment of resistance of the flange is greater than the resisting moment. Whatever the moment which is actually coming on the beam is lesser than the moment of resistance. So the neutral axis lies within the flange. So neutral axis will lies within the flange. Hence the design of T-beam is as rectangular beam. So use the same formula to calculate the AST. Okay, so which you have done for the beams. So 0.87 Fi AST into D. This equation is also there in page number 96 into 1 minus AST Fi divided by BF into D into FCK. Just we have to replace the terms, that's all. So moment, factored moment is 300. No need to calculate for the ultimate moment. So for working moment we are calculating the required steel. So moment is 300 into 10 power 6. So 0.87 Fi is 415. So AST, so area of the steel only we don't know, into 600 multiplied by this one. So I will solve this one. So if I solve and multiply by 1, I will get 216630 AST. So if I solve this one and multiply by this term, I will get 9.989 AST square. So this is a quadratic equation. So I will rearrange this equation. I will take this one AST square on the left hand side, that will become minus, will become plus sign. So 9.989 AST square. So this was plus, actually there is no minus symbol. So if I take to the left hand side, so it will become minus 216630 AST. So plus the term constant is remaining here only, is equal to 0. So you have to calculate this quadratic equation. I think you are done in your beam design. So I will just once again tell you. So just you have to change the mode of the calculator. Next to on button there is mode. Press mode. So then keep pressing mode till you get equation. So I will press 1. So because in equation they are given 1. So then actually unknowns 2 and 3 it will come. Here you have to press this symbol. So next to this one mode, actually there is an arrow mark. Press this one. Degree. So degree will come. So in degree you have to press 2. So if I press 2 degrees, because square, this is a quadratic equation. Substitute the value of this one, A 9.989, okay, is equal to B value. So you have to substitute with the symbol, means minus. No need to substitute for the plus as plus symbol. Minus 21630 is equal to, after entering the value, press is equal to C. So C is 300 into 10 to the power of 6. 300 into 10 to the power of 6. So which is equal to, see, x1 value works out to be 20200. So 20,200. So press one more time equals. So it will come 1486. So that is a huge number. First one was a huge number. Don't use that. So the required steel is 1486 millimeter square. So solving this using the calculator part is very important. So previous problems, so in the design analysis of beams, so I think it may not be there. So analysis of beams, so AST was not there, so you have to use the calculation part. So check in the Google if you didn't get here also. So check in the Google how to solve the quadratic equation using a scientific calculator. So a scientific calculator ಯೂಸ್ ಮಾಡಿ ಕ್ವಾಡ್ರಾಟಿಕ್ ಇಕ್ವೇಷನ್ ಹೇಗೆ ಸಾಲ್ವ್ ಮಾಡೋದು ಅಂತ ನಿಮ್ಮ ಗೂಗಲಲ್ಲಿ ಕೊಟ್ಟರೆ ತೋರಿಸುತ್ತೆ ಅಲ್ಲಿ. ಸೊ ಯು ಕ್ಯಾನ್ ಫಾಲೋ ದ ಸ್ಟೆಪ್ಸ್. ಸೊ ಓಕೆ, so we calculated the area of the steel required. Okay, that's in the problem. So multiple choice questions. So we have come to the multiple choice question. So solving problem is over. The main thing, in order to refresh the course, this will be helpful. So you can read the question. In simply supported beam, the moment near the support. So what will be the moment near the support in simply supported beam? So we are told in the theory, actually, let's see the options. 0, arcing, sagging, both option A and B, that is A and B, 0 and arcing. So actually in simply supported beam, there will be a sagging moment. There will be no arcing moment. So option A and B doesn't work. Actually, near the support, you have to see. If they are given only the in simply supported beam, the beam moment is like that, so you can write it as sagging. But near the support, it is 0. Near the support, the value of the moment is 0. So answer is 0. Okay, we'll move to next question. The actual width of the flange is the spacing of the beam. So options is distance between the adjacent spans. Means one beam is there, adjacent slab is there. So that is the distance between the adjacent span. That is S1 plus S2. They are telling distance between the middle points of the adjacent span. That is S1 by 2 plus S2 by 2. Distance between the points of zero moments. So zero moments will not come into picture. So the option will be, I think. What do you think? So option is actually B. So distance between the middle points of the adjacent span. So we have to actually recap in the session 1 where we have written the top view of this one. So beam and the slab. So there you can see the in that one S1 plus S2 divided by 2. So third one, IS code requirement for T. What is the IS codal requirement? The slab should be cast integrally with the web. Yes, monolithical construction. The web and slab shall be effectively bonded together. So if it is a separate slab, then effectively it should be bonded for the T-beam action. The main reinforcement of the slab, if the main reinforcement of the slab is parallel to the beam, transverse reinforcement shall be provided. Absolutely correct. So all 3 points are correct. The answer will be D, all the above. Next, the compressive stress remains constant. The compressive stress remains constant. So constant means rectangular between the strain O. Everything is same between 0.2, 0.25, 35. So what will be the correct value? I think it's C. So 0.002 to 0.0035. Okay. So between the strain 0.002 to 0.0035, the stress that is the strain will be compression stress remains constant, rectangular part. So just to confuse on the decimal numbers, I have given this question. If the strain is 0.02 is located in the web, then the stress in the flange. So imagine, so 0.02002 level of strain is in web. So then the stress in the flange will be constant and parabolic none. Answer will be constant. Next question. T-beam action does not exist in lintel, deck slab, roof slab, floor slab. See, deck slab also is casted along with the beam. Roof slab is also casted with along the beam. Floor slab. So lintels. So wherever the openings are there, we are going to provide lintels. There is no slab connection. So in lintels, T-beam action does not exist. If dF by D does not exceed, means if it is less than 0.02, and in that case the position of fiber of 0.02 strain will be in what? The position will be in, actually it is web. So make correction. If dF by D value, if it is does not exceed, means less than 0.2, and in that case the position of the fiber of the strain 0.002 strain will be in. Please think whether the answer is correct or wrong. So df by d, if it is less than 0.2, and it case the position of the fiber of the strain 0.02 strain will be in, actually answer is web. So if df by d exceeds, so please recheck the answer for this one. So if df by d exceeds 0.2, in that case the position of the fiber is 0.2 strain will be in web, I have written. So please recheck the answer. I will left to you. So for you guys. Next, in T-beam formula, B is the notation of effective width, actual width, C width of the web, D width of the rib. So it is actually B is the effective actual width. So if BF means effective width. So effective width is the width of the flange over which the compression stress is assumed to be assumed. So in the effective width of the flange, compression stress is assumed to be complex, non-linear, uniform, triangular. So actually we will assume actually for calculation purpose we will assume, but in reality it is complex and it will be non-linear. So answer is C, uniform. So references, thank you all. So I thank all my civil engineering board member, chairman, moderator and subject experts and all my content developer to help me to do the presentation. Thank you one and all.